The Doppler effect was discovered over 200 years ago by a gentleman named Christian Doppler. Let's go through an animation of that. All right. Here we have a sound source that is stationary. And if you're an observer that's standing somewhere down over here, you're going to hear bup, 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 a predictable frequency. Same as if you're standing somewhere up on the top left-hand side, same as if you're somewhere on the right. It'll always be at the same frequency. All right. And that's because you and the disturbance are both stationary relative to each other. And the speed of sound is fixed at 345 meters per second. There is no change there. All right. However, if I end up moving this disturbance, then while you're standing somewhere over here, you don't hear anything, you don't hear anything, you don't hear anything, then pop, 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 pop. Or if you're standing back here, the frequency would be a lot lower of pop, 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 pop. And that's the Doppler effect. Maybe you've experienced it before with regards to, fire trucks driving by you, where you'll notice that the pitch of the fire truck is higher as it approaches towards you, and the pitch decreases afterwards. And this is the sign that explains why it happens. Now at the end, Christian Doppler, he did simplify the formula down to something that looks like this. And if you want to see the mathematical proof for it, I do have a PowerPoint slide that shows it somewhere over here. Okay, how do you create the Doppler effect formula? Here's the mathematical proof, so if you want to pause the video and go through it, then by all means enjoy it. All right, but we got to cut to the chase here. Okay, so supposedly you know that this is the formula. One thing I want to point out is that I flipped this around on purpose because I want you to pause and think. All right, so typical textbooks don't have it flipped around, but I want you to think about how you'd be able to solve this problem here. First off, we're going to assume that the detector, or you're not moving, that you're stationary. So the formula does simplify quite a bit when the observer is not moving. Okay. Now, as the disturbance is coming towards you, you'll notice that it does pitch up. And the only for it to pitch up is that if you had a bigger number multiplied by the reference frequency. F0 is a reference frequency, by the way. And the only way you can get a bigger number is that if the numerator was bigger than the denominator. So, pick your poison, plus or minus. How would you make the denominator smaller? I think you've guessed it. All right. So whenever you use a smaller, whenever you have the denominator as negative, that usually has a smaller denominator, which would result in a higher frequency. And that can only happen if the disturbance is coming towards you. So that I'm going to remind you with, because when it comes to your unit test time, you'll have to know that yourself. There's no reference sheet for that. Okay. So if the disturbance is coming towards you, make sure you use a minus sign. And conversely, as it's moving away, it pitches down. The only way for it to pitch down is if the denominator was much larger. To make a larger denominator, just add the values together. Let's go through a mathematical problem. A car is traveling at 100 kilometers per hour and it honks its horn at concert A. If the speed of sound is traveling at 331 meters per second, what is the apparent frequency as the car approaches towards you and as it drives past you? So it's going to go, all right, so what is the higher apparent frequency and what is the lower apparent frequency? Pause the video, because in 5 seconds, we're going to move on. Okay, so let's go through this. How would we calculate that out? All right, first thing we got to do is that we need to convert everything into meters, kilograms, seconds. So we want to convert the 100 kilometers per hour into meters per second. And how would we do that? All right, well, we get our 100 kilometers per hour, and we're going to multiply it by this conversion ratio. Okay, kilometers per over 1 hour. Well, we know that in 1 hour there are 3,600 seconds. This way we can cancel out the hours. Now if we do our calculations right now, we're going to get a calculation in kilometers per second, but we want it in meters per second. All right, and we know that in 1 kilometer there are 1,000 meters. This way we can get rid of kilometers upstairs and kilometers downstairs, and all we're left with is meters per second. So you pull out your handy dandy calculator and you calculate out 100 divided by 3600 multiplied by 1000, and there you have it. There's your answer, 27.878 meters per second. Now, as the car is approaching towards you, you want to make sure that your v source has a minus sign in the denominator. You can write the minus sign here, or you can write it in the formula. It's up to you. Now, as you're stationary, the detector goes to 0, so you don't need to worry about that term. Instead, you want to figure out the speed of sound, sub it in to the point two variables where necessary, and make sure that your v source, which you'll sub right into here, it has a negative in its sign. Crunch away, and as it's approaching towards you, the frequency should be higher. After all, your denominator will be a smaller number. So the apparent frequency as it approaches towards you is at a higher pitch at 480 Hertz, and as it moves away from you, you're going to have a plus sign in the denominator this time around, and that will make it pitch downwards. There you have it. How about take on this more challenging example? How fast is the car? Alright, so let's say that you hear a frequency of 400 Hertz, but you know that its natural native frequency is at 410 Hertz. How fast is the car traveling? Start off with your givens. Okay, what do you know? First off, if we assume that the temperature is equal to 20 degrees Celsius, then 331.4 plus 0.6 times 20 degrees will give you 12 degrees added on top, which is 300 and, what is that, 43 meters per second. Okay, so the speed of sound is equal to 343 meters per second. Make sure you show your work. Okay, show all work for that. Just trying to cut to the chase there, as you should have done your homework last day. Our reference frequency is at 400 Hertz. So what is our apparent frequency? So our apparent frequency is equal to Vs over Vs plus minus V object multiplied by F naught. At least that's the way how I memorize the formula. If you want to use the textbook version with those letters, by all means with that. Okay. And what we're trying to do is that we're trying to solve for what is the corresponding speed of the car. Sorry, we know F. F is at 410 Hertz. So you can see I'm doing all this stuff real time. Okay, so how we're going to solve for how fast is the object traveling? Well, first off, let's look at this. The frequency pitches up, right? You start off at 400 and you finish at 410, so that means it's approaching towards you. As it approaches towards you, you know the denominator needs to be a minus sign. So at the end of the day, all we're trying to do is take the formula and isolate for V naught. So let's go through that exercise. First off, I can bring F naught over here, so I have F divided by F naught is equal to Vs minus V naught. And the quickest way that I can solve for this afterwards is that, yeah, you could cross multiply and do all that craziness, but you can also just reciprocate both sides. Since the left is a fraction, and the right is also technically a fraction, you could do a quick swap Rooney and you're going to get the same answer. If you don't believe me, try it out. 2 over 3 is equal to, I don't know, 5 over 6. Well, 3 over 2, actually that's terrible, because that's not true. 4 over 6. 2 over 3 is equal to 4 over 6. Well, if you flip it around, then 3 over 2 is equal to 6 over 4. Alright, so you can use this shortcut. So that will give us then FO over F is equal to Vs minus V naught over Vs. You bring Vs over to the other side, so it'll look like this. And since we're solving for V naught, our best bet is probably to bring V naught over here and bring this term over to the right. So we get V naught is equal to Vs plus Vs F naught over F. And if you want to be extra about it, you're more than welcome to factor out your Vs if you wanted to. So Vs 1 plus F naught over F. That's up to you. You don't have to do that next step. Nevertheless, 343 meters per second, 1 plus 400 Hertz divided by 410 Hertz. Pull out your calculator, crunch away through it, and you will get to your answer of 8.4 meters per second. And you can leave it at that. There's nothing wrong with 8.4 meters per second. However, just to give it more context, you may want to do this. 8.4 meters per second times, let's place it as an improper fraction, and we want to convert it into kilometers per hour. So there are 3,600 seconds in 1 hour, and there's also 1,000 meters per 1 kilometer. So 8.4 times 3600 divided by 1000 will give us the equivalent speed in kilometers per hour. Because sometimes we just want that kind of context, right? Doesn't mean that you need to do that on a unit test or exam, but often, especially with driving vehicles, what exactly does 8.4 meters per second imply? To most of us, it means nothing at all. But 30 kilometers per hour, well, try pedaling that on your bicycle, and it's kind of fast. One more cool thing just to share with you with regards to the Doppler effect. If you remember, there was that whole redshift and blue shifting back in grade 9, I guess. And what they're trying to emphasize is that, for example, this is a star system over here. If the star system is moving towards you, then you should expect compressions at the front. All right, and then the compressions will be further separated when they're further away. So if you're standing on the right, it'll be compressed and it'll be blue shifted. Meanwhile, if you're standing on the left compared to the disturbance, then you'll be red shifted because the waves are spread further apart. All right. After all, red wavelengths are much longer and blue wavelengths are much shorter. Okay, so hopefully grade 9 makes a bit more sense now. I guess the one last cool thing to share with you over here is that when we talk about red shifting in astronomy, it's not really red. We're actually talking about infrared. So when you look at the sky at night, it looks pitch black, and that's because you can't see infrared light as a human being. But if you take your fancy DSLR camera and you dissect it and you rip off the infrared filter, and then you start taking pictures at night, you'll see it's just glowing. It's super bright out there. All right, and that's how astronomists, yeah, that's how astronomists are able to, I guess, calculate out and predict that our universe is expanding, because all we can see out there is not visible light, but tons and tons of infrared light. All right, last topic for today is Mach number. All right, it's not a Mach speed, it's a Mach number, because at the end of the day, it's the ratio. It's a ratio of how much faster you're traveling, or how fast you're traveling, compared to the speed of sound. Now, the speed of sound can either be measured in meters per second. Just make sure that the speed of the object is also measured in meters per second. You could also have the speed of sound measured in kilometers per hour. You can convert that if you want to. All right, and that's the case that you need to do if your speed of the object is also measured in kilometers per hour. So just make sure the units match up, because meters per second divided by meters per second will give you no units at the end. It's just a Mach number. So when you're at Mach 1, you're traveling at the speed of sound. When you're traveling at Mach 2, you're traveling at 2 times the speed of sound. Well, let's take a look at what it would look like as an animation. Okay, once again, here's an object that's stationary. No matter where you're standing, everyone's going to perceive the same apparent frequency. Here, the object is moving, but it's moving at subsonic speeds. In other words, below the speed of sound. So yes, there's going to be rapid compressions at the beginning, and then the compressions won't be as rapid afterwards. So the apparent frequency will be a lot lower on the far side. So it's almost kind of like IndyCar racing. All right, but hey, what happens when you're pushing the limits? All right, so let's say you're now traveling at Mach 1. In fact, if you look on the top right hand side, that is telling you the Mach number. So now I'm traveling at Mach 1.02. You hear nothing, nothing, nothing. Then you hear a sonic boom, and that's what a sonic boom is. And yeah, you could go much faster and you get this wonky cute looking picture. Nothing, 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 then now you know. Look at that. Isn't that beautiful? There's a lovely YouTube video that explains all of this stuff here. I'll add it to the playlist. Okay, last question of the day. What is the Mach number of a jet flying at 1800 kilometers per hour with the speed of sound through air at 350 meters per second? Go ahead, work through it. Remember that in order to calculate out your Mach number, you have to divide the speed of the object by the speed of sound using the same exact units. Alright, so your Mach number is equal to VO over VS. So what we want to do is we want to take our 350 meters per second, and there is a shortcut to convert into kilometers per hour, believe it or not. The long way of doing it is for every 3,600 seconds over 1 hour multiplied by 1,000 meters for every 1 kilometer. Alright, you're always doing the same steps over and over again. In other words, this box over here, you're just repeating that same step over and over again. And with your calculator, if you need it, 3,600 divided by 1,000 will always be a multiplication factor of 3.6. So believe it or not, 350 times 3.6 is the fastest way to get your conversion. So you're getting 1260 kilometers per hour in your denominator, and your VO is at 1800 kilometers per hour. So 18 is greater than 1260, so you must be traveling at over Mach 1. You are traveling at supersonic speeds, which ain't good. It really drives animals crazy, drives people crazy, has a probability of causing windows to shatter, and the FAA doesn't approve of it. That's why the only time that you're actually allowed to fly an airplane at supersonic speeds is above water. Now you know.
The sonic boom is not what you think.
I'll let you watch that in the playlist. Catch you in the next episode.